Okay, dear colleagues, I'm glad to see you and hear you. And we start our first seminars, Contemporary Analysis in Partial Differential Equations. The seminar supported partially by Fond and Allier. And let me introduce our first talking today. It's Georgy Kitavtsev, professor from Middle East Technical University, and his talk is recent advances in analysis of critical points of Landau homogeneous energy in 2D and 3D. So please, Gregory, we look here.
Good afternoon, or just good afternoon, everybody, and thank you very much for inviting you to your seminar. It's a pleasure for me to present the results I mean, not the results, but kind of give a spot on some topics which I'm doing research, and so I've chosen this topic. You might know that we have, of course, at least 2 other extra topics which I'm doing with Roman Taranets since already quite a lot of number of years. So I just thought that it could also might be interesting to know what else can be seen in my research, and that's a research topic which I did actually around 5 years ago in Bristol with Valery Slastikov, Jonathan Robbins, Artur Zarnescu. And that time it was kind of a new topic for me on liquid crystals, because before I came there I didn't know almost nothing about liquid crystals. But it turned out that it's kind of topic which easily can be adopted by people doing PDs and people doing calculus of variations. So hopefully you will get some new interesting information after this topic, which you might also be interested to kind of look for research in these topics. On the other hand, it's kind of also a topic which might attract theoretical physicists, people doing mechanics, because a lot of kind of methods which are used in theoretical physics and mechanics are also explored here. So that's what I will also try to demonstrate in my talk. So my talk is not pure mathematical. In fact, there will be not too much proofs and not many theorems at all, but it's kind of overview what mathematicians can do about liquid crystals and especially Q-tensors, applications to liquid crystals. So let me start with just motivation. So liquid crystals, of course, it's a very hot topic before and nowadays, because all mobile devices now use liquid crystals screens based on a touch sensor technique, which is based on basically on liquid crystals. And of course, it's a topic which attracts a lot of funding from and grants since years already, and probably also without some things which I will show you today, the modern technology of mobile phones wouldn't exist, because in parallel mathematicians also helped physicists to develop devices. But again, I will be more on the physical side, not on applied one, and the model will keep as simple as possible, so you can understand liquid crystals kind of interpolation material between solids and liquids, because in solids, I hope you can see when I show some, you can see my mouse. So liquids is kind of fully isotropic originally material, where basically the properties of the material doesn't depend much on the direction in which you are looking through, and also it's a flowing material, so it's basically not constrained to some reference configuration, in opposite to crystal solids, which are strictly more or less fixed to some reference crystal lattice, and basically they are very kind of orientation dependent. So properties of crystal solids depend in which direction you look through and in which direction you deform them. So it's a basic physics which everyone probably knows, and liquid crystals incorporate both features in a different, say, fashion. They can flow, but they can also depend on a certain characteristic directions inside of the material, principal directions, like in solids. And they demonstrate also all physical properties differently depending on the direction on which you apply. Say, all tests, say, magnetic field, electrical field, light propagation, everything depends on the direction, but it's not like in the solids where you have just three principal directions. Everything can become very patent, like in the experimental picture here. Very patent, where you see that resembles very much what people see in phase transition theory, right? You have grains, inside of these grains you have kind of orientation of liquid crystals in this blue or green areas is more or less aligned according to certain preferred orientation. And between these grains you have interfaces. In fact, in physical experiment you see these are not interfaces, it's also thin kind of thin layers in which orientation changes quickly, like a diffuse interface approach in cantilever, for example, right? But besides that, there are also defects. So this kind of stars and knots where you intersect, where you intersect black stripes, basically they're called point defects. Again, that's just approximation. In fact, you see in the experiment, that's again just subdomains which are small sized domains which are kind of at the border of black stripes. So what we will do in this talk, we will approximate this knots by point defects, this black stripes by lines, which are called disclination lines or disclination walls. Yes, and I will try to explain you how such patterns occur and how. I don't speak much about dynamics actually, so if you're interested, we have some partial results also on dynamics, and not only we, but I can also give you literature and associated parabolic PDEs and also associated results on existence and dynamical properties of the solutions. But so today I will be purely static basically, and we'll speak about what is called steady states or critical points of the energy. So, and another feature, I mean, what is interesting, of course, it's the phase transitions here, that for high temperature, this becomes like a pure liquid. And for some under below certain critical temperature, this forms these patterns, and also that's the way how they found the liquid crystals were found experimentally by Austrian physicist, sorry, I forgot his surname, but at the end of 19th century, he basically made experiments with complex fluids, and he exactly, I think, observed that light propagation speed changes abruptly when you cool down the material, and also all optical properties and flowing properties of the material changes. So and then in the next basically say 60 years, people try to classify such materials to understand actually are they fluids or some intermediate materials. But then came basically fundamental works of Leslie Erickson on one side and DeGenis on the other side, and these are two approaches which you can basically explore by investigating liquid crystals. So, but let's start first with define what is defect. So defect actually is nothing new for you. Anyone who does kind of defects in fluid mechanics can understand the description of defect here. So if you approximate the direction of the liquid crystal by the director field, by the vector field, which is called n, so n is a vector in 3 dimensions here actually. So k is just what is called degree of the vector field. So all the vector fields have similar boundary conditions, which given by this vector nk. So you're just rotating your director field and generating in the middle the corresponding defect. So what is the degree of the defect? It's also the same as more or less topological degree of the map. But here I'm just using simple physical definition. So the degree of the defect is defined by the ratio. So if you rotate in the material domain, so let's say in a circle, anti-clockwise with the angle 2 pi, you look at the total rotation of your director field along this circle and divide the total rotation of the director field by 2 pi. So, and then this gives you index of the defect. So, for example, perfect what is called hedgehog. On the left, you rotate by 2 pi in the material domain, and you also rotate director field by 2 pi. So you divide 2 pi by 2 pi, you get 1. So on the right, you have -1 defect, because if you rotate anti-clockwise in the material domain, you basically start from horizontal direction, but then you move clockwise. Your director rotates clockwise by the same amount, 2 pi. So it means -2 pi over 2 pi gives you -1. And such defects probably you also see in classical potential flow, right? So what is interesting here in U, the so-called rational defects, which are not integer defects. For example, 1/2 and -1/2. So in the left, you moving on a circle, you rotate your director only just by angle pi, right? And then you have a jump along this red line. So this red line can be very approximately corresponded to what you saw on the experimental picture with this black stripe. So because here you jump, your direction jumps by jump pi, and then you can imagine, of course, especially if you say work with Landau Ginsburg or Hiller type energies, right? So that you produce kind of singularity which has essentially infinite energy here. So you cannot kind of extract logarithmic singularity here or some singular term from the bulk energy. So you have essentially, due to this jump of the director along this line, you have essentially infinite energy producing, right? If you have a gradient term in your energy. So similar, if you have a -1/2 defect on the right, you have actually 3 what's called disclination lines. So let me see. I'm not sure if along all of this you jump, but yes, you also produce kind of line singularities, which are called disclination lines. And then this demonstrated for non-integer defects, a standard kind of vector field energies are not suitable because they don't incorporate such configurations, and such configurations are important, in fact, also in the simulations. So they are not just kind of artificial interest. And that was a kind of motivation of the people in Bristol. So they did some work before I came to understand this kind of rational defects. And the right model, the right way to model them is Q-tensor energies instead of vector field energies. So again, the motivation is to describe non-integer defects with finite, which should have finite elastic energies. Second is to resolve disclination lines. So because sometimes along the disclination line, sometimes you just change the direction of n. So you don't actually, so your jump is just because you just, instead of pointing director to the right, you just point it in the same direction, but to the left, right? So physically it's the same, because your molecule, if it's symmetric, if the molecule of liquid crystal is symmetric, it doesn't matter where is the head and where is the tail of the molecule. So the direction can be chosen upwards or downwards, or from left to the left or to the right. So physically there is no difference, but that's pure mathematical kind of problem which should be resolved. And another phenomenon which is separate one, but it's also why the people believe it is important, it's so-called biaxiality phenomenon, because what you are looking at such macroscopic models, of course, not on a single molecules, right? You are looking on a kind of averaging substances. So on a macro scale, in a sense, right? So, and this turns out that there is no kind of, on macro scale, might be not really preferable, say, direction at all. Might be just like in mechanics, there might be principal directions. So, like also in experiments, they saw there are principal directions along which the speed light, so light speed is just different, right? And this happens at each point of your material. So that means instead of vector, you should have at least matrix, right? And then the principal directions will be just eigenvectors of this matrix. So that's how the genius came to the idea of a Q-tensor. And actually, that's one of the achievements for which he got a Nobel Prize in '92. It's a Q-tensor theory for liquid crystals, among others, of course. So Roman also knows that the genius was very active in liquid films, right, theory, in liquid films, but he's kind of one of the greatest physicists of 20th century. So that was his idea to introduce Q-tensor, and the idea actually is not for physicists, again, it's quite natural. So instead of, so because if you average, everybody knows, if you average vector field, because of these constellations, plus minus n, you can get 0. So then you need to look at the dispersion, right? So that's kind of Q-tensor is the second moment of S, where S is director field. So minus 1/3 identity is kind of just normalization or adjusting of the mean, right? Times rho xs. Rho is just probability function, probability distribution of molecular orientations. So it depends on the point, material points in your domain and the direction S, which lies on a sphere, S2 in three-dimensional space, right?
Excuse me, what means the nature fractional 1/3? How appear?
Yeah, it's a good question. I think it's just from it's a normalization of rho. So rho should be normalized to 1, right? So if you integrate over sphere, you get some extra, because it's a not linear space, you get some extra area of the sphere. So that's, I think, as far as I remember, that's how this coefficient comes into play. That's one thing, but maybe I'm saying it wrong, because in fact it can be just pure mathematical thing. In order to obtain what you will see on the next slide, it's you will see Q-tensor, which is symmetric. Q transpose is Q, and trace of Q equal to 0. So I don't exactly remember this. It might be that they subtract 1/3 identity just exactly to get trace to be 0. Otherwise, you get trace which is constant, and it's something like this. So it just can be for practical reasons. But it's for sure that rho should be normalized to be 1. It's probability measure. On a sphere. So saying in short, you're looking not on say on a directed field, you look at the dyadic product of directed field with itself, and then you, in each material point, you integrate over all possible orientations of this dyadic product. So, and then as a total, you get the matrix for each material point X. You get, if we're in a three-dimensional space, it's a 3x3 matrix, and it's called Q-tensor. And then it starts basically a very standard thing, which also people in mechanics do. You just find eigenvalues, eigenvectors, call them principal, say, directions and principal values. So, for example, these lambdas can be physically also corresponding to light speed propagation. That's one of the way also to derive Q tensors physically. But the new thing, which was not previously in mechanics, is that the trace of Q will be 0. So when I showed once this slide to physicists, they said, okay, it's also not a new thing, it's kind of connected maybe with incompressibility of material, right? You can also interpret this as an incompressibility condition of your strain tensor or something like that. But I'm not particularly sure. But that's additional thing which you get, and that's related to the constraint on rho, that it has integral 1 over sphere. So then each of such Q tensor in material point X can be represented as a parallelepiped with 3 directions, orthogonal directions, n1, n2, and 3. And lambda 1, lambda 2, lambda 3 is just scalar coefficients associated with these directions. These are called scalar order parameters. So lambda 1, lambda 2, lambda 3 scalar order parameters, n1, n2, and 3 vector order parameters. So physically, n1, n2, and 3 shows actually you need just, in fact, you need just due to this kind of conditional eigenvalues, you just, I mean, also without them, you need just to know n1 and n2. These are 2 principal directions. So physically, you can say that locally your material point, liquid crystals try to orient either in direction n1 or in the direction n2. Then lambda 1 and lambda 2 will give you just a proportion between orientation along n1 and n2. They are called scalar order parameters. So because if lambda 1 is close to 0, say that means along n1 you actually do not align too much. You probably align more along n2. But again, everything what I say is just my personal interpretation. And of course, it's just, now it starts more mathematical part than the physical, right? So how you can interpret, for example, this transition between liquid and liquid crystal state. So liquid state called isotropic state, it's when your all eigenvalues are zeros. You don't have preferable direction. So that means your Q tensor is 0, and if you solve kind of hydrodynamic equations, you will solve just Navier-Stokes equation without Q tensor part. But if you below, say, isotropic temperature, isotropic to a liquid crystal transition, you generate non-zero eigenvalues, you will solve kind of Navier-Stokes equation coupled with Q tensor parabolic equation dynamically. So, and there are 2 states, which one is called uniaxial state, when 2 eigenvalues are the same, say lambda 1 and lambda 2. That means you give just one scalar degree of freedom, right? You just take lambda 1 as a degree of freedom, then lambda 2 is equal to lambda 1, and lambda 3 is minus lambda 1 minus lambda 2. So you have one scalar degree of freedom, and in fact, you can also show that you actually just need direct product of, to know direct product of n1 with n1. So you just need one principal axis to know, because then you can find n2 and n3 from lambda 1 and n1. That's why it's called uniaxial state, because that means basically you really have kind of determining direction of your crystal which you can use. And these are still not a fully vector model, right? It's in two places. First, everything depends on dielectric products, right? So if you change the sign of n1, for example, you don't change the dielectric product n1 times n1. So that means you don't have this problem with the jump between plus n and minus n. Moreover, you also have the scalar parameter. So it's this model which has one vector parameter and one scalar parameter. Okay, so that's a kind of material part. So let's now come, how can we define energy of such physical energy of these materials? So there are actually huge literature. I just was looking in the morning again to refresh my memory of all these kind of derivations which I used for deriving the energy and the corresponding differential equations. So, but what we used is a so-called joint or free invariance both in X and Q spaces. And that's encoded in this equation. So if you basically apply a certain transformation, which is rotation or mirroring P on Q, you should also apply at the same time P inverse transformation on X. Then the energy of the object on the left of Q should be the same as the energy of the object on the right. That's the invariance which we used in our article, and this leads to what is called several elastic constant energy. So if there are another way to define this invariance, you just define basically that energy should be separately invariant with respect to X and Q transformation. Then you get what is called one constant approximation or Dirichlet energy. So Q times the Dirichlet energy would be, so in the second line, this would be just 1/2 or L over 2 square of a gradient of Q. So this would be classical Dirichlet energy for Q tensors. But because we have slightly relaxed invariance, we get a second elastic constant M, which multiplies divergence Q squared. Again, I don't know what is the right analogy in the hydrodynamics, but that's a gradient part of the energy. It has two constants L and M. And there is a bulk potential, so that bulk potential is more similar to what is called Allen-Kahn or Kahn-Hilliard or Landau-Ginzburg potentials, right? It's a fourth order potential, but potential in Q. And again, because of the invariance of the invariance of the energy due to this space Q, material Q spaces invariance, it depends only on an invariance of Q. So invariance of Q are trace of Q, which is 0, trace of Q squared, trace of Q cube, right? And because it's, I mean, it's, I don't know why there is no trace of Q4, but it's a fourth order energy. And it's kind of, that's where Landau theory comes in, right? So it's kind of Taylor expansion of bulk energy and elastic energy around around thermodynamical equilibrium, right? Where Q is isotropic is 0. So here implicitly, Digenis assumes that Q is small, but that's assumption which is used, I believe, in all material theories. Kahn-Hilliard or Allen-Kahn and so on. So again, the main differences to classical models, so that Q is a matrix first. Energy depends actually on traces of powers of Q, bulk part, but it's a fourth order, it's a double well potential, right? You can also think about it as a double well potential, but in the Q space, which is 5-dimensional space, right? So matrix 3×3 has symmetric one, has 6 components, but because its trace is 0, it has 5 degrees of freedom. So such a interesting phase space where you define double well potential for the bulk energy, and elastic energy has two terms: one of gradient of Q squared and divergence Q squared.
Excuse me, but this depends on sign your constant A, B, C.
Of course, yes. That's what I exactly wanted to discuss. What are the signs of the
I remember double well potential appear in special case when A, B, C connect with some special connection, not arbitrary case. Yeah.
Yeah. So that's what. No, I mean, if you replace trace of Q, if you replace by just formulating by some scalar function, right? F. So you have a quadratic term, cubic term, fourth order term. So that means it's a fourth order polynomial. And yes, of course, the double well potential will be not all possible shapes of a fourth order polynomial, right? So, but you see we have assumptions here on A. So first A is linearly proportional to the distance to the critical or this transition. I'm not sure that this T0 star is exactly transitional phase transition temperature, like in van der Waals model, right? But it should be close to it, right? So you see, it's negative because
Georgy, your energy is dimensionless or not?
originally not, but all of these are dimension. A, B, C, L, M are dimensional one. But then we will rescale them to be dimensionless. So that's what I'm trying to do here. A is negative because you are below the transition temperature. It's proportional to the negative and not very high because it's close to T0 star. So B is either negative or zero. So that means probably it's connected exactly to your question that we need to replicate double well shape. That's in this assumption. Right? Because when B is equal to zero, you have kind of double well shape. Right? I guess C should be positive, right? And then you have kind of like Q squared plus Q to the power 4, which is double well, right? It's a Q.
Yeah, interesting.
No, A is negative, C is positive, so you get Q4 minus Q squared, right? You take 1 Q squared out, you get Q squared minus 1, you get plus minus 1 or 0. It's a double well, right? If
Yeah,
B is 0.
traditionally we have only first and third term in classical Kahn-Hillard or Allen-Kahn equation.
No. In classical, what you call first and third, it's a pressure term. It's already a variation of energy. So if you differentiate this FB with respect to Q, you get first term, you get the third one, right? And you get the second one, you are right. So if B is equal to 0, you will get traditional Kahn-Hillard. That's what I'm
yeah.
So B is negative. It's a different case here. It's a very good question how it appears. The simplest answer is just because it's allowed. It's not forbidden. That's the answer. It's allowed, and that makes the game interesting, right? So if B equals 0, you see minimizers will be biaxial, and they will be constrained. Basically, trace Q squared also will be constrained to just ratio minus A and C over C. And more or less, the set of minimizers will be isomorphic to its sphere S4. So again, because it's a tensor model, you don't have just single minimizer. You have to the error invariance. You just spend the whole sphere if you have one minimizer, right? So, but when B is smaller than 0, then minimizers are drastically different. And because if you minimize, in this case, you will get what's called uniaxial minimizers, which has preferred direction n and preferred scalar degree of order S plus, so it's kind of eigenvalue in this case, which is related in such fashion to the physical parameters B and A and C. And that's the changes game a lot, and the set of everything will be changed, the set of steady states, depending if B equals 0 and B smaller than 0. So maybe you are right, so B equals 0 is more traditional to more resembling what happens in Ginsburg-Landau, for example, and B smaller than 0 something new in this theory. But besides, you also have so-called coercivity conditions on parameters L and M, because you need that elastic part, right, should be bounded from, or should be positive definite form in a quadratic form in gradient of Q. So this condition implies that L should be positive and M should be larger than minus L over 4. Okay, so that means basically you have also constraint on relation between M and L. So this minus 3 L over 4, you will see on the plots, which I will show you on bifurcation diagrams. It's a kind of left boundary of all bifurcation diagrams. So, again, so you can also formulate these defect boundary conditions, which I showed you on the second slide, in terms of Q tensors, because you just take the vector fields, which are used for K defects, and you take dyadic product of them with itself, and multiply with optimal parameter C plus, so you generate boundary conditions, K radial symmetric boundary conditions for Q tensors. The corresponding minimizers or steady states, which satisfy this Q radial symmetric boundary conditions, will be called K radial symmetric critical points, or shortly KRSCP. So that's our abbreviation, I guess. It's not common, physically common here. It will never be common. And actually, it doesn't matter. So, okay, so that's then we say that the critical point is KRSCP if basically it has this kind of joint material Q tensor invariance, right? So if you rotate by angle phi your point X, you should rotate your Q tensor by angle K phi over 2. Sorry, it's not a joint invariance, it's just the symmetry of the boundary conditions. It's inherited symmetry of the boundary conditions. But in fact, it means just what I showed on the first slide. It's just this. If you have a preferred, if it's uniaxial minimizer, you have a preferred direction n, and if you plot n vector field, it will have these shapes of hedgehog, these discrimination lines, and so on. So it's a just generalization from vector field theory to Q tensor field theory. So then one elastic constant approximation, so pure Dirichlet energy, when second elastic constant is 0, was quite already investigated before I came to Bristol, and it's also investigated in the last few years. I just did add here literature, but the number of literature is quite extensive for one constant approximation. On the other hand, I should say for two constant approximations, there is no too much energy even now. Even I can just count maybe 2-3 articles which discuss, and even more, there is only one article by Chinese guys on numerical investigation, but not too many articles also on numerical results, which are the main point of my presentation today, to show you the kind of variety, huge variety of different configurations which you can find with two constant, elastic constant energies. Okay, so I should mention, of course, the work of John Ball, which was one of the main mathematicians driving this field since 80s. So he worked on Odion-Frank energy. So Argiv Zarneska was his PhD student. So then with Argiv Zarneska, they started to investigate Q tensors and got the main first results on Q tensor energies, existence and of steady states, dynamical models associated with Q tensors. So that you can look at the, that's John Ball is the most probably referred author concerning liquid crystals and Q tensors. So let me switch to what we did in the article, which I referred to with Valery, Argir, and Jonathan. So we looked at basically K radially symmetric critical points of our energy under boundary conditions, which has the same symmetry, and just because they're radically symmetric, you can reduce your Q tensor energy to just kind of energy depending on finite number of scalar functions, which are called W0, W1, W2, W3, W4. And for doing that, these W's will depend just on the radius vector, right? On the distance to the region, while in order to obtain this representation, you need to choose a suitable basis in your Q tensor space of symmetric traceless. So by Q tensor space, I mean just a linear space of symmetric traceless or trace zero matrices, right? 3 by 3. So if you do a clever choice of the basis, for example, like shown here, which is exploring basically 3 vectors, and I should say now that I'm switching kind of quasi 2D situation, so where basically you assume that everything changes in a plane, and along the third direction, nothing changes. So it's basically invariantly translated in the third direction, which is spanned by vector E3. Then n is the radius vector in a plane, m is orthogonal vector in the orthogonal vector to n, and they have kind of this K symmetries. So then if you split in such clear way your basis, the coefficients W's will just depend on the radius vector R. Right, so you will exclude from W dependence on the polar angle in the plane phi. And then if you minimize your Q tensor energy under such representation, you basically go a little bit ahead. You get, instead of Q tensor energy, you get just energy, scalar energy, depending on 5 scalar functions: W0, W1, W2, W3, W4. Just a moment, I need to answer. Извиняюсь, она, у меня сейчас доклад идет. Okay. Okay, so we have energy which is huge and not visible, but you can split this in two parts. Again, elastic one, so the first two lines, and the potential one, the last two lines. So again, I don't comment on this, and you don't need to think about what this formula means. It's just reduced, what is called reduced radial energy, which is more tractable analytically and also more tractable numerically. And among the minimizers, sorry, by the way, I don't know how much time do I have remaining for the talk. Hello?
No, maybe 10 minutes enough.
So yeah, okay. So yeah, 10 minutes should be fine. So what is interesting here, you can just look at special configurations. So so-called two-component solutions, which just have configurations W0, W1. Three-component solutions, which just have three W's and other zeros, and full one, which has all W's non-zero. So why you can do this? Because if you set, say, W2, W3, W4 to 0, you see you will kill a lot of terms here, and you will get just very nice energy quadratic with respect to two components, W1 and W2, which kind of coupling of one dimension to, say, one-dimensional Allen-Kano-Cahn-Hilliard equations in one dimension, right? Because everything depends just now on everything is radially symmetric, it depends just on R. Of course, if you write all Lagrange equations, you just get not even PDEs, you just get two ODEs, right? And then you just solve these ODEs in a two-dimensional space, dynamical system, and you find everything what you're interested in: steady states, the instability, and so on. So that's how people approach investigation of steady states in such complicated models. Just look first on simple solutions. So what's about, by the way, general result? It's done again in our article. So and we show that k radially symmetric critical points of the energy exist only if k is not equal to. So in fact, here you will not have non-integer defects. You just have one integer defect equal k equal to. So that's basically Hedgehog configuration on the first slide. So, and in this case, if you look for k equal to, you have your components to satisfy certain mixed Neumann-Dirichlet boundary conditions at 0. So you have boundary value problem. You have conditions at origin and conditions at the boundary of your disk. So they come out kind of some of them natural conditions, some of them Dirichlet conditions imposed at the boundary. So that's just we follow here. No assumptions anymore. Just once we fixed energy, just mathematics, Euler-Lagrange equations, natural conditions, minimization. So everything is strict. This is a strict result about existence. But at the moment we're dealing with ODEs because everything is radially symmetric, right? So now, so my part was mostly to do numerics for this, to calculate these minimizers numerically, and representation, how you represent minimizers, you represent them using this kind of schemes of Q tensors blocks. So it's kind of for your mesh discretization in each discretization point, of the mesh, you plot a parallelepiped, which represents visually Q tensor at this plot, right? It has two principal directions, and the lengths of the sides of the parallelepiped Li's are scaled according to your eigenvalues of the Q tensor, more or less. So that's so-called two-component solutions. One of them is global minimizer in the regime which we shown here. So usually we take radius of the disk fixed. We take A and C constant to be fixed and L to be 1, and we vary usually M. So here when M is 0, you get that you have global minimizer with two components W0, W1, non-zero. By the way, what means global minimizer here? It's a global minimizer not of the radial energy, the global minimizer of the whole energy, Q tensor energy. So when I did this numerically, I minimize the whole Q tensor energy. And then just look how many components I get in the minimizer. And you have also local minimizer, so which is stable both in a full energy and in the reduced one, but it has energy which is higher than the Q2 minus. So by proceeding further, you can also get free component solutions. Some of them have observed in physics before. So for example, this Q3 is a so-called radial escape solution, and Q5 has all 5 components non-zero. It's a tilted radial escape. So radial escape means you start at the boundary, align perfectly along the boundary. Once you approach the origin, you grow the E3 component outside of the plane, right? Because your problem is actually 3-dimensional. So yeah, it's invariant. It's translated in the third direction, say trivially, but your Q tensor basically can have the third direction still. So and then it's, if you come to the origin, you just align with the E3 direction exactly at the origin. Such solutions appeared also in Ginsburg-Landau models. And the Q5 is actually the one which I call the new one. I am not sure that somebody observed it before. It's called tilted radial escape. Besides radial escape going up, you also can, you see, you have a tilt, right? In the horizontal, in the phi direction. So the nature of this guy is not fully clear, and I'm not sure if somebody saw it in other models. But and also we have what is called 2-1/2 defect solutions. These are not radially symmetric solutions, but they can be split in two solutions which have 1/2 defects, which I showed you on the first slide. And also there is a tilted guy. By the way, I'm working now in the case B equals 0, which Roman said might just be relevant more to Cahn-Hilliard model, right? To tensor generalization of Cahn-Hilliard model. If you now consider B smaller than 0, something changes. So you lose tilted solution, you still have kind of 2-1/2 defect solutions. And the dependence on the second elastic constant basically amplified if you look at the biaxiality, so-called biaxiality measure of your solution. So what is biaxiality measure? It's measured on the left diagram. It's basically when you are red, your Q tensor is actually biaxial. And when you're blue, you kind of like a vector field model. You don't have two directions, you have just one direction. So your Q tensor is uniaxial, right? So when you increase M in this example, you spread the region around defects where you essentially should be biaxial. And that's quite important for physics, by the way, because if you speak with a physicist, by the way, with Oleg Lavrentovich, for example, from Kent State, which is a main guy nowadays for physical experiments and theory of physical theory. So he would say that they don't see actually biaxial regions, maybe in the experiments, or it's very hard to observe them because there's this kind of, it's epsilon core, right? So that M now allows to increase this epsilon core to potentially to make them more feasible in the experiments. But all of this is kind of, it should be verified physically. Still not clear counterparts in physical experiments of these solutions. Okay, so that's a joint bifurcation diagram. I will just show you two bifurcation diagrams and I will stop. One for B equals 0. And they become really fun because if you do this carefully minimization of Q tensor energy, you get a lot of different solutions, and you need to decide first who is basically minimizer, who is a critical point like saddle, and then also to decide what type of bifurcation you observe. So that's kind of, don't blame me afterwards, but that's kind of our approximation for the bifurcation diagram. Because if you do, so you here fix, you have two parameters, radius of the disk and m is a second elastic constant, and you fix everything else, and you start, say, from large m and go to the left along the fixed radius. You observe several bifurcations. So when you have very large m, your minimizer is two component, q2 minus. In the first blue curve, you generate saddle, what we believe saddle or fault bifurcation, where you generate one stable local minimizer Q2 plus minus. 2 means again two component solution. Then along this parabola, black parabola, you do pitchfork bifurcation, where you generate actually not two solutions but four solutions. So Q free and so-called Q tilted, non-radially symmetric. It's because you can bifurcate not only, say, in a radial energy, you can also bifurcate in the full space, Q tensor space. So you can have a kind of radial solution bifurcated, but you can also have unstable modes in the full state. That's why you bifurcate these two guys. Right? It's in fact four guys, right? Because pitchfork bifurcation has four solutions, but they are symmetrically related. So then along the green one, we believe there is a kind of transcritical bifurcation where Q2 minus becomes also non-radially symmetric. That's called vertically non-radial symmetric without tilt. Then the magenta curve is kind of not a bifurcation line, it's an interchange of global minimality. It's a kind of second order phase transition between two minima. So here you interchange tilted non-radial symmetric with vertical non-radial symmetric. So then again, along the black one, if you go to the left, you bifurcate pitchfork, and you remain with three solutions, Q2 plus minus, which is now global minimizer, and Q2 minus is local minimizer. And then if you go even more to the right, you do another saddle point bifurcation, fold bifurcation, and you lose Q2 minus. So such, again, I don't claim that that's a final picture, but it's just shows how interesting and complicated the things becomes here, even statically. And that's case B smaller than 0. So again, if you go from the right, you start with Q2 as a global minimizer, you generate actually transcritical bifurcation, I guess. This blue line now is transcritical one. No, it's not. It's again saddle one, sorry, but it's a saddle in full space because you generate non-radially symmetric solution. Then what is interesting here, if you cross the black line, which is I guess it's again pitchfork, like on the previous one, but you can generate either Q3 or Q5. So you can generate Q3 as a radial escape, or you can generate tilted radial escape depending on the radius of your domain and on dimension of m. Okay, and then along the green lines, they just transform into each other. Q3 transforms into Q5, probably transcritically. Okay, so but you see two bifurcation diagrams are quite different for B smaller than 0 and B equals 0. Nevertheless, they have common features. So again, global minimizers are shown in black type, local minimizers in blue type, and what's called saddle points of the full energy, but at the same time, which are local minimizers of the radial energy, are shown in red. So that's how we detected them. If you minimize the full energy, you will never detect these red guys, right, Q2. But if you minimize the critical, so reduced radial energy, you will get them because they are radially symmetric and they are local minimizers of radial energy. So that's, I probably will stop here, and that's kind of main reference to our work. And if you are interested, of course, I can also give you some other reference depending on which type of part of the talk you are more interested in. Okay, thank you very much for your attention.
Thank you, Georgy. We also thank you very much for your nice talk today. I really, but I don't know how it's possible to do via online. So thank you. And please, colleagues, questions, comments.
I have one question connect with your main theory. Please show your main theory about existing.
Okay.
Okay. Restriction L plus 4 over 3m grade 0 appear due to non-negativity of energy.
No, it's a kind of you need to have low bound of your energy, right? So you have parabolic part of the energy. So if it's pure directly, if m is equal to 0, you have low bound which is 0, right? But if m is not 0, you need to have low bound from the energy, and that's given by the scarcity condition. Because for m smaller than -3 L over 4,
no, your restriction is not physically. It's not physics.
Yes, it's mathematics. As I told you, after once we fix this energy, it becomes everything is just mathematics, nothing, no calculus and variations and PDs.
Thank you.
So, yet questions, comments? No. May I ask you also previous your slide where is A, B, C? If I correct understand, is this constant is follows from the physical point of view, yes or no? It's so I keep in mind restriction for this constant.
Yeah, so some constants like A are clearly from physical origin, so they're just proportional with certain coefficient to difference between
but
the critical.
for B and C constant, it's the physical restriction or mathematical. I keep in mind so non-negativity B and positivity C.
Non-negativity of B, I would say that's mathematical restriction. Exactly as Roman said, kind of to resemble double potential, but I'm still not sure. Maybe it's also physically motivated. And that's a very good question, actually, about C. Even I don't know. We need to look at the literature. If it's
Okay.
This should be possibly clear that C should be positive.
Yeah, it's from
mathematically. But how much is it? I mean, everything is here is not so, again. You should look at the articles of Oleg Lavritovich to understand these issues, because here experience sometimes far behind than the mathematical theory.
Thank you so much. Yet questions, colleagues? Maybe remarks? No? So, okay. Thank you very much again, Georgy, for your nice report today. And dear colleagues, we finish our seminars today, and about our next meeting, we will announcement to you via email. So, and take care of yourselves and goodbye. Thank you.
Okay. Thank you again for inviting.
Thank you.
Bye.
Thank you.
Bye. Bye.
Bye.